So current will stop flowing as a result of electrical charges in both these half cells, right? Here, as a result of oxidation, positive charge got developed, negative charge on the rod, right? Here, as a result of reduction, negative charge on solution, positive charge on rod, right? So charges got developed, electron movement was stopped. As a result, current will stop flowing, right? And this happened due to the charges that got developed in both the half cells, right? And one thing where oxidation is taking place, we call this electrode as anode, right? And here where reduction is taking place, we call this rod as cathode, right? So where reduction is taking place, we call it as cathode, and where oxidation is taking place, we call it as anode. Now, since current has now stopped flowing, right? There is no current in galvanic cell, no electron movement means no current. So now what we can do so that this current should again start flowing in the galvanic cell, because main aim of the galvanic cell is to produce electrical current or electrical energy as a result of chemical reaction. But at this situation, we have come across a situation where current has stopped flowing due to these charges. Now, to make this current again flow, we need to remove these electrical charges. These positive charge here, negative charge here. We need to remove these charges. Now, how to remove these charges? There is something called as salt bridge that will now come into picture, right? Salt bridge, it's a bridge because we connect these two half cells with that bridge. I'll just show you that diagrammatically. This is how the salt bridge looks like. It's an inverted U tube, right? It's an inverted U tube that contains solution of an inert electrolyte like potassium bromide or potassium chloride, potassium nitrate. These are all inert electrolytes, and it contains the solution of inert electrolyte, and it also contains agar-agar solution, right, which makes it a thick paste, a jelly like thick paste of agar-agar solution, right? So this is something it looks like here. If you look at this, right, it has a porous plug at its end. So this is connected between these two half cells. Since it is connecting these two half cells, we call it a bridge. Like a bridge, a normal bridge connects the two roads across the river, right? Similarly, this salt bridge connects these two half cells, right? And this salt bridge contains inert electrolyte, say potassium chloride, so it contains potassium ions and chloride ions, right? And we have a porous plug here. This porous plug will not allow solution to move from these half cells into the salt bridge, or it will not allow solution from this salt bridge to flow into these half cells, right? So it will connect the two half cells without the solutions getting intermixed, right? So this porous plug will only allow movement of these ions. If this contains potassium chloride inert electrolyte, right, so it has potassium ions and chloride ions, so it will only allow potassium ions and chloride ions to move out of these porous plug into these half cells. So let's see what these ions will do. Since this contains negative ions, chloride ions, right, and positive ions, potassium ions, and we have a negative charge in this half cell in anode where oxidation takes place, and we have a negative charge in the reduction half cell where reduction takes place, right? Negative charge as a result of reduction reaction at cathode. So at cathode we have, in the half cell where reduction takes place, we have negative charge. Here we have positive charge. So now let's see how salt bridge will act to remove these electrical charges. Since we have negative charge, this negative charge in this salt bridge, so this negative chloride ions will move out of the half cell, out of this salt bridge into this oxidation half cell or anode where we have positive charge. So these negative chloride ions will neutralize the positive ions in the oxidation half cell, right? Positive ions, that is positive charge is due to zinc ions, right? So the negative chloride ions will neutralize the positive zinc ions, right, in the oxidation half cells. Similarly, we have potassium ions in the salt bridge. These potassium ions will move into the cathode, into the reduction half cell, and will neutralize the negative charge on this, in this half cell, right? So this is how salt bridge will keep the electrical neutrality of the solution. It will keep solution in both the half cells electrically neutral, because when charges were produced, the cell stopped working, no current was flowing. So we connected a salt bridge, right, that connected these two half cells without the solutions getting intermixed due to these porous plugs, right? So these half cells will maintain their electrical neutrality with this salt bridge, because this salt bridge has inert electrolyte, right, and it has oppositely charged ions. The ions will move out of this salt bridge into these half cells and will neutralize the solutions, right? The positive zinc ions would be neutralized by chloride ions, and negative sulfate ions would be neutralized by potassium ions. This is how it will maintain the electrical neutrality of the solution, right? So, and it has one more function. Since it connects these two half cells, what it does is it completes the inner circuit. It completes the circuit, right, by completing this inner circuit, by creating this inner circuit, because in the outer circuit these electrons are flowing. When we connected the salt bridge, inner circuit got created and this entire circuit got completed, because through this inner circuit ions are moving, right? So it connects the two half cells and completes the cell circuit. It maintains the electrical neutrality of the solution. And the third most important point is, in the absence of salt bridge, transfer of electrons from oxidation half cell to reduction half cell takes place for a moment, right? And then cell stops working due to the charges that develops in the two half cells, right? Positive and negative charges, as a result of oxidation and reduction reaction. This is very important function of salt bridge. So once these charges are neutralized, we will again have electron movement, right? And due to electron movement, current will start flowing. When current will start flowing, you have deflection in galvanometer, showing that current has again started flowing, right? Now, there are some important things that we need to remember. Okay, one thing, since we have in both the half cells, if you see, there is something known as redox couple, which it says oxidized and reduced form of same substance present together, which take parts in the reaction, and the reduction half cell reaction is called redox couple. Since in this half cell we have this zinc rod, this zinc rod basically is in contact with its own ions. Here copper rod is in contact with its own ions. Since this is a copper rod, the solution contains copper ions, so we say copper rod is in contact with its own ions. Here we have zinc ions, so zinc is in contact with its own ions. These are ions. Similarly, here we have copper rod, then copper ions. So zinc is the reduced form of zinc ions, and zinc ions is the oxidized form of zinc neutral zinc atom. Similarly, here copper is the oxidized form of copper metal is reduced form of copper ion. So these are called as redox couples. This is a redox couple, right, and this is again a redox couple. Redox couple is where we have oxidized and reduced form of the same substance together. This is a redox couple, right? And another thing that we need to consider here is, okay, one thing, in any galvanic cell we have reduction half cell always on the right hand side, and the oxidation half cell always on the right hand side, right? And as per IUPAC convention, we'll do this in the next video lecture. As per IUPAC convention, the reaction is always written as reduction reaction, right? And the electrode potential, we'll understand what electrode potential is. Okay, let's just do it. I just introduced you to electrode potential. We'll do that in detail in next lecture. Since in this is a zinc rod that has negative charge on it due to this oxidation reaction, right? So this is the, we have negative charge on this zinc rod due to oxidation reaction. These electrons got deposited on this rod, right? And this solution become positive because these positive ions which resulted from oxidation of zinc entered into solution, and these positive ions made this solution positive. So we have like this positive charge in this solution. So we have one layer of negative charge, another layer of positive charge, right? We call it as electrical double layer, right? And similarly, if we talk about reduction half cell, due to the reduction reaction, these copper ions gained electrons from this copper rod, making it electron deficient, so it developed positive charge, right? Similarly, this solution as a result of reduction reaction got excess in sulfate ions which were negatively charged, so solution developed negative charge. So this is another electrical double layer, right? Since these charges, we have these, when we have charges separated, right? So due to these charges, we have potential difference, right, in this electrode. This is one electrode where oxidation is taking place, right? This is an electrode where due to this oxidation reaction, these electrical charges got developed, and due to these electrical charges, when we have charges separated, right, we have potential difference develop, right? So due to these charges, potential difference will develop between this rod and solution, right? In a way, this potential difference developed due to this electrical double layer, and this electrical double layer resulted due to this oxidation reaction, right? So we call it as oxidation potential. This is an electrical potential, electrode potential, which is known as oxidation potential. Similarly, this electrical double layer which resulted due to this reduction reaction, positive charge on copper rod, negative charge on this solution. So this resulted due to this. So again we have charge separation in this reduction half cell. Now due to this charge separation, potential difference will get developed between this rod and solution. This potential difference is known as reduction potential. Right? This is your reduction potential. Reduction potential is, by definition we know its reduction potential is ability to get reduced, and oxidation potential is ability to get oxidized, right? Since oxygen has more ability to lose electrons to get oxidized, so it generated oxidation potential. Similarly, copper ions have high ability to gain electrons and get reduced, right? So it has high reduction potential, which got generated as a result of reduction reaction or high reduction potential of copper, right? So oxidation and reduction potential. And one thing, this oxidation potential is always, we say both these are equal if we talk about reduction. This is the oxidation potential. We know oxidation potential of zinc is high. What about its reduction potential? Its reduction potential would be equal to its oxidation potential but opposite in sign. Same is for this half cell, copper. For copper, the reduction potential, we know the reduction potential of copper is high. So what about its oxidation potential, the ability to lose electron? It would be equal to its reduction potential but opposite in sign, which would be very less. Experimentally, the oxidation potential of zinc was found to be 0.76. Oxidation potential of zinc is 0.76. Reduction potential of copper was 0.34, right? So what would be the reduction potential? What would be the reduction potential of zinc? Reduction potential of zinc would be equal to its oxidation potential but opposite in sign, that is minus 0.76. Oxidation potential of copper would be, it would be minus 0.34, right, which is very less, we know. Its potential to get, so the potential to get oxidized for copper is very low, it's a negative quantity, right? So oxidation potential is always equal in magnitude but opposite in sign, right, of reduction potential. So we say oxidation potential or reduction potential would always be equal in opposite but opposite in sign of reduction potential. This is how these two are related. Now one thing, this electrode, this is a electrode that consists of this half cell, a beaker that has electrolyte solution, that has an electrolyte and a zinc rod dipped in it. The zinc rod is in contact with its own ions. This is known as one compartment. Similarly, copper is in contact with its own ions. This is the second compartment, right? So we call it a compartment. We have two compartments. And how many conductors we have? This zinc rod, these are metal conductors. Zinc and copper rods are conductors, metal conductors. This copper wire is a conductor. We have ions in the solution, right, which conduct electricity. We know movement of ions. Ions are charges. Movement of charges cause electric current. So these ions are ionic conductors. These are metal conductors, right? Zinc, copper and copper wire are metal conductors. These ions in solution are ionic conductors, right? So we are done with this, right, working off galvanic cell, right? So I hope all this is clear to you. Thanks.